In this video, we're going to go through how to use the Virtual COM Port device class for an STM32 microcontroller. We'll go through the basic hardware elements, then look at the setup in CubeIDE, configuring the peripherals as well as the clocks, and then I'll show you how to transmit and receive data using our USB Virtual COM Port link. As you'll see, this is pretty straightforward and very useful in many scenarios. If you want to transfer data from your device, for instance the STM32 microcontroller to a host, this could be a PC. If you want to use it as a terminal for logging or any other debugging procedures, this is very nice as it replaces a UART to USB transceiver, because oftentimes the USB peripheral is directly integrated into the STM32 silicon, and it's very straightforward and quick to set up. Before we move over to looking at the firmware setup and CubeIDE setup, let's have a brief look at the schematic to see how you could do this for your own hardware designs and how simple it is setting up STM32 microcontrollers for USB. Now keep in mind there are some quirks and differences between the different STM32 microcontroller lines, so sometimes you will need external pull-ups, sometimes you need a crystal, and sometimes you don't. For this particular STM32H7 microcontroller, all I'm doing is I'm rooting out PA11 and PA12, which are the relevant USB-DN and USB-DP signals of the USB 2.0 full-speed differential pair, and routing them to and from a USB Type-C connector. You can see I'm tying DN1 and 2 and DP1 and 2 of this flippable USB Type-C connector together. Because we're running USB 2.0 full speed, this is completely okay. I do add external TVS diodes, so ESD protection. We can see D200 and D201. Although the ST microcontroller does have internal ESD protection, I always recommend to add external TVS or ESD protection right at connector interfaces. For power and power delivery, for dumb USB-C power delivery, so to speak, for each CC pin, so the communication channel pins, I'm using a 5K1 pull-down resistor with 1% tolerance to ground on each of these CC1 and CC2 lines. And I'm getting 5 volts from my host PC. In this case, I'm using a laptop, supplying the power via VUSB, and that's actually then feeding to a 3.3 volt regulator, which is powering my STM32H7 microcontroller. We'll look at an app note in just a second, because this is a rather straightforward connection. We just have a simple USB differential pair, no pull-ups, no additional circuitry other than some ESD protection and some filtering. But for some microcontrollers, you need an explicit external 1.5K pull-up on the USB-D plus line, and I'll show you where you can find that in just a second. For this particular STM32H7 microcontroller, I actually do not need an external crystal if I want to run USB 2.0 full speed, because the internal oscillator is accurate enough to drive this so I can do crystal-less USB. However, I typically strongly suggest always adding an external crystal, because you'll get better timing accuracy unless you really want to minimize your bill of materials, unless you're really cost cutting. So for instance here, for the high-speed external crystal, I've added a 25 MHz crystal oscillator with the suitable load capacitances. But you can, in certain cases, if the datasheet tells you that you can run crystal-less USB, you can go without using a crystal. But in many times it is required, so do keep that in mind. To find more of this information where you do need external pull-up resistors if you can run with or without crystals, I'd strongly suggest checking out application note AN4879 by ST, which is an introduction to USB hardware and PCB design guidelines for STM32 MCUs. And that goes over the main STM32 series, so Ls, Gs, Fs, and so on. We can see which devices support full speed or high speed, as well as seeing if we have an embedded pull-up resistor on the DP line for specific microcontrollers. Most of them aren't yes, but some series, for example this F302 B and C series, has a footnote 2, and if we look at that, it needs an external 1.5K pull-up resistor. This is to a voltage between 3 and 3.6 volts, and oftentimes you might want to tie that to a GPIO pin, which you can toggle, which will make your device renumerate, which is very useful and helpful for debugging. We can also see crystal-less USB features, and you can see this only exists for certain and very specific devices, and sometimes only in device mode, not in host mode. So please make sure to check out this application note, because it is rather useful. A huge thank you to JLCPCB for sponsoring this video. I had these digital guitar effect PCBs manufactured and assembled by JLCPCB, and they did an absolutely fantastic job. JLCPCB provides easy, affordable, and reliable PCB and PCBA solutions, which really empowers electronics engineers to develop projects efficiently and quickly. JLCPCB is super easy to use. We simply have to click on Instant Quote, add our Gerber files if we just want PCBs, or if we want assembly as well, we upload our Gerber files as well as bill of materials and pick and place files. Their pricing is incredible due to large-scale production, which reduces their and our costs. We can get 8-layer PCBs, for example, with 50 by 50 millimeters in dimensions for only $2. I've had a super good experience with JLCPCB. I can get my PCBs fully assembled back in about a week's time, which is amazing. Not only is their lead time super fast, but their quality is top notch as well. So I'd highly suggest you check them out. Links will be in the description box below. A huge thank you also to Altium for sponsoring this video. If you'd like to give the powerful Altium 365 platform a try, make sure to follow the link in the description box below or go to altium365.com/yt/philslab and you can get yourself an Altium 365 free trial. Altium 365 brings many impressive features to Altium Designer, such as collaborative design reviews, mechanical co-design with SolidWorks, Fusion and more, manufacturing collaboration, ease of BOM management, and much, much more. If you'd like to check out in part some of the cool features of Altium 365, you can also go to my GitHub profile and my GitHub IO page, pms67.github.io, and check out some of the example hardware designs that were shown on the YouTube channel here. With the Altium 365 viewer, you can explore the boards in your own time and in real time. You can look at the 3D models and you can scan through the PCB layers as well as the schematics on some of the designs as well. I'll leave links in the description box as usual. Let's now move over to the STM32 CubeIDE setup. We have some basics to set up as usual. That is our external crystal oscillator, our serial wire debug connection, and then we'll simply set up USB 2.0 in full speed device mode and add on top the USB Virtual COM Port driver that is very nicely just provided by ST and pretty much works straight out of the box. Depending if you're using the STM32 Virtual COM Port on a device that has CubeIDE installed or not, you may have to install the Virtual COM Port driver separately, particularly if you're on Windows, which you can download via a quick Google search looking for STM32 Virtual COM Port driver. It should natively run on Mac and Linux, I believe, but for Windows with a CubeIDE not installed, you will need this driver to make sure your Windows system sees the STM32 microcontroller in this mode. What I've set up first is going to RCC, enabling the high-speed external clock, and I'm clicking on Crystal Ceramic Resonator. For the STM32H7, my serial wire debug is actually under Trace and Debug on the bottom. Click on Debug, and you can enable whatever debug interface you have, if that's JTAG or serial wire debug. I happen to have serial wire, but I also have my trace output, so I've selected trace. It doesn't really matter for this video. Then all we're going to be doing for this video is sending and receiving data. We're not actually going to be toggling any other peripherals or controls such as LEDs and so on. We're receiving data and we'll be sending it out. So all we need for this video is a USB connection. So going to connectivity, depending on your microcontroller, it'll be something called USB. In this case, it's USB on the go or OTG_HS. So this is actually the high-speed peripheral, which we can run in full speed mode using the internal full speed physical layer. For high-speed mode, we would need an external ULP PHY. But for the sake of this video, just internal full speed device. You can either use dual role, host, but we want device only because we're connecting to a host PC, so that's what I've selected. Then we have a few different parameter settings we can enable, disable, and change. Speed, we only have one, which is full speed. If we want to enable the internal IP DMA, which oftentimes can be a good idea, for H7 microcontrollers, this involves a bit more work because the memory region for this particular DMA is in a memory region that is not actually accessible by the DMA, so we have to change the linker script, and that's a bit too much for this video, and it really depends on what microcontroller we're using, so we'll keep that disabled for now. You can enable VBus sensing, various options such as link power management, but the default settings as we have here, I haven't really changed anything, are completely fine. You will most likely want to enable the interrupts. Those are under the NVIC settings. I've enabled all of these interrupts, but other than that, that's all I've done. And CubeIDE has already shown me which pins we need to be using in our schematic, and that's the ones we saw earlier, so PA11 and PA12 for USB, DN and DP. We could leave it at that, but of course we want to make our life easy, so that's why we're going to be using a pre-made driver by ST. We can access that by going to middleware and software packs, scrolling down and clicking on USB device. Now there's some very, very nice other drivers we can use, and we've explored some in previous videos, such as the Human Interface Device Class or DFU, but for this video we're looking at Communication Device Class, which is our Virtual COM Port or CDC for short. There are various parameters we can also change here, such as buffer sizes, maximum descriptors, and so on, as well as the device descriptors. Now, device descriptors mainly, we have VID, so vendor identifier, and PID, product identifier, and I would just leave them as default because if you want to change them, you will have to pay for them most likely going through the USB IF, or you can also sometimes request free PIDs from ST themselves. You can put in a request if you'd like to have a device with a unique product identifier or PID. You can also try and check out PID.codes. As they state here, if you're a maker, hobbyist, or startup company producing your own USB device, you can request a product ID from them for free instead of paying roughly $6,000 going through the USB IF to get your own PID VID. So something to check out if you would like to make something into a product that uses USB and ST microcontrollers. But for now, we'll leave our device descriptors and our parameter settings as they are. In clock configuration, depending on what crystal sources you are using, if you can or cannot use crystal-less USB, you will have to change various settings here. For now, I'm just running my input frequency at 25 MHz, selecting the high-speed external crystal as we saw in the schematic. I've adjusted my PLL values to give me the maximum core frequency for the H7. Now, this isn't exactly needed, but I've just done it for the sake of. And if we scroll a bit more down, another important section is actually the USB core clock, which can vary, and I'd recommend checking out the datasheet and reference manual to see what values this can be. But typically, you will need to be around 48 MHz for this core clock. If we look at the clock sources, we can see these can be derived from PLL1 or PLL3, but this STM32H7 also has an external 48 MHz oscillator, which is accurate enough for USB full speed. So we could also go with the internal oscillator, and we do not need to connect an external one for this specific STM32 microcontroller. Keep in mind, this is not always the case. What I'll be using is the external crystal oscillator with the PLL values that I derived for my 25 MHz high-speed external crystal. With this setup, we can click Save, and this will then auto-generate most of the code we need, and then we need to add in a few details to properly configure the virtual COM port and then try and receive and transmit some data. Before we move over to writing some code to implement the RX and TX sides for this COM port driver, you can also check out the code in your own time if you check out my GitHub profile under github.com/PMS67 and navigate to the IFX Guitar DSP repository and look at the COM port branch. This is the code we'll be using and we'll be writing here to look at both the transmission and the reception sides for the COM port driver, as well as any other setup we have to do. So you can check this out in your own time. Links will be in the description box below. After having saved the CubeIDE IOC file, the whole project structure has been generated automatically for us, and there's not terribly much we have to do to get the COM port now working. By default, USB device.h is included in main.c, and if we scroll down to int main, we can see the mx USB device init function being called, which initializes and registers the class of the CDC port of our virtual COM port, and that will then call an initialization function. What's then left for us to do is to set up the COM port correctly, so that is the line coding, and then fill in the blanks for the receive and transmit functions. We'll start with transmission, where we'll just periodically send some random data and see if we can receive that on this host PC. Then we'll do a program which receives data and then spits back how many bytes it's received at what time, just to show something very, very, very simple, which you can then expand on for whatever application you need this for. On the left-hand side in the Project Explorer, we can see quite a few folders have been created, such as the middlewares, where we can see the STM32 USB device library. But for us, also interesting is the USB device folder under app, and we can see cdcif.c and the corresponding header file. If we go to cdcif.c, on the right-hand side in the file outline, we can see we have various control functions, initialization functions, and so on. cdc init hs, ignore the hs for now, this is just because of the name of the peripheral. We are actually running in full speed mode, not high speed mode, but this is grouped together. This cdc init function is actually implicitly called once this mx USB device init has been run and the class has been registered, so we don't have to call that ourselves. What we do need to handle are the transmit function, so we need to call that if we want to send some data, and that takes an array of uint8 type variables, as well as a length of that array or of that buffer. The receive function fills a buffer and tells us how many characters we've received, so we can use that then to process that data in that buffer that's been received in an external function, for instance. And this receive function is automatically called by the USB driver, USB handler by ST, so this is very, very simple for us to then use. We could pretty much use the transmit and receive functions straight away, but on many instances of host computers, for instance Windows machines, we do need to fill in some detail in the CDC control function. In particular, we need to fill in the set line coding and the get line coding case statements. This will then tell the host PC what baud rate, how many stop bits, parity bits, and so on we're running at. Now, for virtual COM port, this is just emulating, and that won't actually change very much of the performance, but we do need to feed back a nominal baud rate, parity bits, stop bits, and so on. Again, please check out the Git repo. I will be going over this quite quickly. What I'll be copying over is in line 98, just this line coding type def. So I'll set a nominal baud rate of 115/200, which is pretty common. 1 stop bit, no parity bits, and data bits are 8 at a time. And this is our line coding. And this happens to be a line coding define already in the driver. Then going down to the control HS function, we need to fill in the line coding cases where from the host PC, we are receiving information of what the device should configure itself in terms of the COM port, in terms of bitrate, format, parity, and data bits, and so on. And again, this is just taken from some pre-made example by ST, and then something similar for the get line coding function, where we pass our default line coding back to the host. And this again is taken simply from an ST example, but we do need to add this in because otherwise our example code might not work on all systems. So that's something pretty much you always have to add in. With that in place, we can now finally focus on transmitting some data. For transmitting data or writing data from the device to the host, I will be using the CDC transmit function. And this is terribly simple. All we have to pass it is a buffer, an array, and then tell it how many characters or what length that array has. Now, although I'll be passing text into this buffer, you can of course just send raw bytes depending on your speed and system requirements. Going back over to main.c, what I'd like to do is create a global buffer that can be used by the CDC transmit function, as well as define a generic buffer length. So I'll go into private define at the top and main.c, and I'll just create a define that a typical USB buffer length is 128 bytes. Then I'll just create an array which has the length of the define we have previously. And this define length is just a placeholder. It is the maximum length this buffer can be. This could be up to 2048, but to just conserve memory, I'm making it a bit smaller. Additionally, we need some sort of measure of how long this buffer will be, and this depends of course how you're transmitting data, but I'll be using the STM32 function, which returns the actual length of characters that are filled into a buffer. So I have my array here and my buffer length right below, and now I can copy over the CDC transmit function define, and we can see also it returns the result of the transmission. So if there's an error or if the transmission was okay, and of course you can handle those cases depending on your situation. Then in the main while loop in main.c in int main, we can fill in a buffer. And for that, I'll be using the STM32 function. For instance, I could write something like so, where I'm using the STM32 function, which fills a buffer with a certain structure. In this case, I'm using the USB TX buffer, which is actually a uint8t type, but STM32 expects a char array type or char pointer type, so that's why I'm just casting it to make the compiler happy and not throw a warning. The maximum length we can fill this buffer with is USB buff length, which is our define, and then I'm just writing the structure of what I would like to have filled into this USB TX buffer. I'm doing a long unsigned int with a carriage return and a new line, so I can clearly separate on the receiving end every time data is sent. And all I'm filling into this long unsigned int is the HAL get tick function, which returns the number of milliseconds since boot or startup, simply speaking, of the microcontroller. The return of this STM32 function is the actual buffer length, so how many characters we've used for the USB TX buff, and that'll be helpful then when we transmit the number of characters to the CDC transmit HS function. So after I've filled my buffer, I can then of course send. So I'll copy over and paste the CDC transmit HS function, which takes the USB buffer as well as the USB buffer length, how many characters we actually want to transmit, and it's as simple as that. Now, if I just left this in the while loop like so, of course it would transmit at the maximum possible speed, which I don't really want, so I'm going to put in a HAL delay of 500 milliseconds. Now I can compile this, and we can see, of course, there's an implicit declaration warning of function CDC transmit HS. That is because at the top of main.c, we need to include USB CDC-if.h. Now I've added that in, I can recompile, and there we go. We have no warnings. Let's see if this works. So to do that, I have the USB-C connector connected via USB Type-C cable to my host computer. I've got my ST-Link connected to the Tag Connect port of this board, and all I have to do is now click Run, which will upload the code to the board. We're getting a message saying we're setting up a virtual COM port, so the device has been detected. If I then go to my Windows Device Manager, going under ports, we can see a new serial device has appeared. This is port COM7, and this is important to know because when we want to talk to our ST, we will need to specify COM7. In terms of software, I'm using HTerm as my serial monitor. So if I click on refresh in HTerm, this is a free program. We can select COM7, baud rate 115/200, data bits 8, stop bits 1, parity none, and I can click connect. Now we're connected to our ST microcontroller, and as we can see, every half of a second, we're getting the current millisecond runtime on the MCU, and we can see the difference or the delta between each of these entries is about 500 milliseconds, given the accuracy, of course, of the timing. You can see I've also changed the option to new line at carriage return and line feed. as we specified in our transmit buffer. So that's why I'm getting a new line every time I'm getting a reading. So very, very simple to transmit and set up a virtual COM port, transmit data from our device, our STM32 microcontroller, to a host, as we can see here. And of course, now you can customize this transmit function to whatever you want. You can send raw bytes, you can send debug messages, you can turn this into a console, whatever you want. But transmitting is of course only one half of the story. Now let's look at reception. Now that we've tested transmission, we of course want to look at reception as well. And for this, we go back to this USB-D cdcif.c file and look at cdc receive hs. This function is pretty much fully customizable, and it gives some indications of what we need to do to receive packets. In essence, the CDC receive HS function is called automatically by the virtual COM port driver running on the ST microcontroller, and that then takes or passes an array or a buffer of bytes and tells us what length of data has been received. After we've processed this data, then what we can do is then set the pointer to the receive buffer of our USB driver and then enable the reception again, wait for the next amount of data to be received. Of course, you might want to process the data that's stored in buff before you re-trigger receive packet and set RX buffer. You might want to have some sort of flow control. The way this is done now, as soon as we've received a packet, we're waiting for another packet straight away. You might want to handle that a bit differently. For us, all we're going to be doing is copying the memory or copying the buffer contents of the received buffer into a different memory location and then instantly re-triggering the receive packet command, as is shown here. Pretty straightforward. This of course assumes there is some time delay between receiving packets and we're not maximizing our bandwidth utilization. Jumping back to main.c, other than our TX buffer and TX buffer length, I've now added some more variables for our receive buffer and our receive buffer length, which we will copy into once we hit that receive function or once that receive function is called. And I also have a USB RX flag that we can then do something with. For instance, we will set this flag once we've received some data, and then we can process that data and clear that flag again. Very, very crude, very, very simple, but I hope it shows the basics. Other than that, I've written a tiny USB RX callback function in main.c, which we will call from this CDC receive function. That simply takes the same buffer, the same length from that receive function. We perform a mem copy and we set the buffer length and we set the RX flag to 1. Pretty much nothing new, nothing different than the actual receive function, just move that over to main. Then in CDCIF, I'm just signifying that there is an external function called USB RX callback that we can then call in USB CDCIF. Then in the receive function, all we have to do is before we restart the reception of the packet is call our USB RX callback, and we'll pass in buff and we'll pass in len. So it's just a straight feed through from the CDC receive function that's automatically called on data reception. We call our callback and then we restart the packet reception. Of course, again, kind of crude, simple enough for this application. Now, scrolling back down into int main in main.c, looking at the main while loop, I've replaced our previous transmit code with something slightly different. I have an if statement checking if the RX flag has been set and if we have a non-zero value in the RX buffer length. Kind of redundant, but that's what we're doing. We're checking if there's any data there. Then we're recording our timestamp, so how many milliseconds have elapsed. And then again, we're using the snprintf function to fill our TX buffer and set the TX buffer length. Now, rather than just recording the time now, I'm doing something, well, not terribly fancy, but I'm splitting this up into minutes and seconds. So I'm converting our millisecond timestamp into minutes and seconds using the following formula. And also I'm printing out, I'm sending back to the host PC the number of bytes we've received of data, sending that back. So we'll get a timestamp, plus we'll get how many bytes we've received of data. Very, very simple example, but just to illustrate how we can receive and transmit data. After that, we will then call the CDC transmit function again. Again, same as before, using the transmit buffer and the transmit buffer length. And then we'll clear the RX flags and the RX buffer length so that we can wait again for the receive function to be triggered, the callback to be called, and the RX flag to be set, and the USB RX buffer length to be a non-zero value. Again, very simple, just to illustrate a point. Now we can compile and upload this code again using the run button. Checking our device manager again, we've re-enumerated as COM6 now. So if we go back to hterm, our serial program, I'm going to reset the port or refresh the port list. We'll select COM6. Let me just clear received and clear sent, and now click connect. Now, of course, nothing will happen until we send some amount of data, which I can do in this control box at the bottom. So let's send one character. I'll just click A and press enter. Now we can see we have a minutes and seconds formatted timestamp being sent back and the number of bytes being sent back that our ST microcontroller has received. Because I've sent just a single A, of course I'll just expect 1 byte of data that we've received. If I write hello, that is 5 characters, and press enter, we can see a new timestamp because of course the microcontroller is continuously running and we're getting 5 bytes of data back. What I can also do is click debug, and we can actually look if the contents of the USB RX buffer are what they should be, other than just receiving the correct number of bytes. So what I'll do, I'll set a breakpoint in our RX callback and click continue. Back in HTML, I'll reconnect. I'll send a new message, for example, test, click enter, and you can see in the background, we've hit the breakpoint. We can hover over USB RX buff len, which is 4. And if we hover over USB RX buff and expand the first elements, we can see we receive TEST, so test, in the first 4 positions of this buffer. So this looks like our reception is working fine, as it should be for this very, very simple example. Thank you very much for watching this video. I hope it was helpful, and I hope it showed you how quickly and easily you can set up a USB Virtual COM Port as well as the CDC driver on an STM32 microcontroller. The procedure is very, very similar across all different STM32 microcontrollers. Luckily, ST typically provides pre-made USB drivers for this, and transmission and reception can be very, very helpful. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date to any latest embedded systems, hardware, PCB design, and firmware videos. Thanks again for watching, and I hope to see you in the next one. Bye bye.